or something else. As we learn in Gen Chem, all nitrates are soluble in water. Silver nitrate is soluble. You can work with it. That's why we use silver nitrate. Okay? Silver nitrate can also be used as a test. Which compounds below would give a positive silver nitrate test? The positive being the formation of the precipitate of the silver halide, which is insoluble. Which one of these will give a precipitate of silver halide? They're all bromide, so silver bromide.
First one? Yeah.
Well, the first one?
Mostly silver.
First one? Second one?
First one.
Why would the first one give us precipitate of silver halide?
Most acidic.
Oh, it's resident stable. No.
First one can't be. It's only second through
Well,
the.
the answer is only second, third, and fourth. The first one, no.
It will not.
Then the third one.
It will not ion.
Chemistry-wise, what's going on here? When the how do you get forming of the silver bromide?
The bromine attacks the silver.
And then
Then leaves.
leaving group leaves. Okay. What type of carbon can a leaving group leave from? Tetrahedral is on page 1 at the top, first line. First line. It's not a tetrahedral carbon. This bromine is not ionizable. We use that term in the lab, right? It's a test for ionizable halogen. It's not going to leave. You don't do SN1, SN2, E1, E2 on this guy. Not a tetrahedral carbon. We could have, should have, but didn't point that out for a third time. But if you go back to the first substitution handout, anybody got a substitution handout? First page of the outline. What's the very top line say?
Tetrahedral carbon.
Read it loud.
Tetrahedral, please do the substitution of a tetrahedral carbon.
And a tetrahedral carbon, yes. Ain't a tetrahedral carbon. Game over. We're not doing any chemistry with this guy. Leaving group's not on a tetrahedral carbon. All right? The other three will give a positive silver halide because the bromine will be stripped out. It'll be caused to leave and go complex with the silver and make silver bromide. Which one of the three over on the right would be fastest?
Middle one.
The question is really, which one's going to ionize fastest? The middle one. Yeah. Not only is it tertiary, it's better than tertiary, it's also, the cation would also be resonance stabilized, right? What is that? Number 2. What was number 1? What are we doing here? We're under G.
Oh, so it is
G1 was using silver.
See, we can change it.
G is how to facilitate ionization. One way is to use silver ion.
I thought it was use a Lewis acid.
To what?
I thought G1 says use a Lewis acid.
Silver is the most common Lewis acid for your halides. There's plenty of others like antimony, aluminum. What's another way to make ionization faster to promote it? Another way is solvent. Use a polar solvent. It's another way to promote ionization. Look at these two reactions. Okay? It looks like we're doing, what type of mechanism is going on here? Bigreacer substitution because the bromine is being replaced by this oxygen, right? Under my hand's bromine on the starting material, but now it's the oxygen substitution, right? SN1 or SN2?
SN2. SN2?
SN2 requires a strong nucleophile. Do you see a strong nucleophile? No. This is this text, this is a solvent. Is this a strong or weak nucleophile? Strong. Anions or sp3 nitrogens? It's neither of those. Weak. Weak nucleophile. SN1. Okay? SN1 plus HBr is a byproduct. Okay? Repeat reaction there. If you do this, let's go back. If we're doing SN1, what's the rate determining step? What's the main rate determining step? Leaving group leaving. Ionizing. Right? Boom. It just has to leave and we get here. We're under G. Ways to make this faster. We could include some silver ion. That would make this faster. Another way is solvent. If you use a polar solvent, such as acetonitrile or DMSO, these were listed on the solvent sheet back in August. Those are polar solvents. I would recommend you look at the structure of these. They are polar. This reaction can occur. If you try to do this reaction, though, in a solvent like hexane, which you know is nonpolar, the reaction probably is not going to work. Why is the solvent doing here? Well, the polar solvent is facilitating formation of a polar ion, where hexane would not facilitate that. Just like ACl, it's covalent. But what happens if you put it in a polar solvent such as water? It will ionize, right, and form H plus Cl minus. Polar solvent does this. What if you put ACl in hexane? Will it ionize? No, it will stay covalent. It will stay gaseous. Polar solvents promote polar ions. Okay? So this is the idea of using solvent to promote your ionization. Make sense? Okay, that was G1 and 2. Next topic here, deuterium isotope effect. A neat way to determine if an elimination reaction is E1 or E2. Again, we're doing a variety of miscellaneous things here at the end. Look at this reaction. It's a lot like the one on the quiz. Take this guy with pyridine as a base. We're doing an elimination reaction. We eliminated HBr from the starting material. It's shown as pyridine has taken the H and the Br minus is there, so we can show this salt. Elimination, yeah? Is it E1 or E2? You don't read anything yet. What do you think? E1 or E2?
I think it's E1.
E1?
Yeah.
Why? Based on what?
The product is Satesep.
Are you saying that E2 cannot give Satesep?
It can, but E1 always gets Satesep.
I agree, but E2 often gives Satesep.
Is pyridine strong enough? And you said pyridine was borderline.
That's the main question. Is it strong enough to do E2 or is it not strong enough? So how can we tell? We're going to do a deuterium isotope effect. That's how we're going to tell here. First off, before we get to that, we already knew one way to tell. We could do kinetic studies. For example, what if we double the concentration of the pyridine upon repeating the reaction? What if we doubled this and the rate did not change? What does that tell you about the mechanism?
E1.
Must be E1 based on involved in rate determining step. So that's one way to tell. You'd have to go to the lab and do some. But if we double the concentration of this and the rate doubled, then we know it's E2. The base is involved in the rate determining step. Right? Well, what's another way? Another way is to do deuterium isotope study. In elimination here, the beta hydrogen is removed, right? Ultimately, that H is removed. I agree there. Let's think about this. In which mechanism, E1 or E2, is the beta hydrogen removed in the rate determining step? E1 or E2? Or both? Which mechanism is the beta hydrogen removed in the rate determining step? E2. Because what's the rate determining step of an E1? Same as SN1, which is leaving. That's it. Make cation. Yes. And in E2, this H carbon bond is broken in the rate determining step, but not in E1. What you can do here is change this to a deuterium. That would require going to the lab, doing some experimental chemistry. Now do the reaction and look at the rate. Now, we need to know this. A CD bond is stronger than a CH bond. It's from the so-called mass effect. If deuterium has a higher mass, it's going to make a stronger bond. I reckon that just goes back to some physics. Okay, CD is strong. I think it's about 7 times stronger. Unless I'm confused. There's a 7 there somewhere. I think it's 7 times stronger. That seems big, but it's stronger. Since it's stronger, if the reaction is E2, what will this being a D do to the rate?
Increase it.
It'll make it more difficult, and thus slow the rate. Because breaking a stronger bond in your rate determining step is more difficult and thus slower. What if it's E1? Will making that a D have any effect at all? No. Because the rate determining step does not involve breaking that bond. It will make breaking that bond slower, but you're slowing up a fast step. And it's like, who cares? Changing the fast step doesn't affect the overall rate. So this is what you would do. You would come up with a... How do you put a D here? Well, there's some sophisticated chemistry. It may be difficult. Actually, in lab. On paper, it's easier. Okay. And then do. So we're looking at the effect of changing this H to a deuterium, which is an isotope. So it's called a deuterium isotope effect. You look for a deuterium isotope effect. That's explained down here. Does it make sense? Did we get it? Yeah? You often see deuterium used in tests, etc. I've used it before, right? Usually we just consider just an H, right? Here, though, we're saying it has a different bond strength, and thus it can affect the rate determining step of the E2. So, I think we covered that. By the way, deuterium drugs. Was that in here?
Yeah, it's at the bottom.
On the very back? Yeah. Just an application. Applications are kind of what we're here for, yeah? There's a drug, HIV drug here. I'm not that familiar with it. It looks like a peptide type of drug. Okay? You'll talk more about peptides in organic 2 when you do carbonyl chemistry. Peptides. Make this even bigger, you get the proteins, right? This drug. When humans are given this drug, it's metabolized by placing an OH here. You're essentially slipping in an oxygen between the C and the H over there. Okay, so it's called hydroxylation. Hydroxylation destroys the drug activity. It's no longer a good drug after this happens. So the drug company wants to slow this process down in the body. You do not want it to be hydroxylated. Okay? Well, in the hydroxylation, the CH bond has to be broken. Now, very often you'll see drugs that have like a halogen here, like a fluorine. They'll just remove the CH bond, and the CF is more difficult to break. And so it will keep that from happening. But in some cases, maybe you don't want a halogen there because that can hurt the drug activity. You want to keep it real small. So instead of H, they have, I think it's shown here, they've replaced this with a deuterium. What do we know about the carbon deuterium bond strength? Stronger. It's going to be more difficult to break. More difficult to get this metabolite, which we don't want. Not really shown there, but the use of deuterium in drugs is actually fairly new. I mean, it's been known for a long time, but never really used in drugs. That's an example of going to the stronger CD bond to keep something from happening in drug design. Yeah? Let's finish this up here. Okay, looks like the last page. Hopefully we've done these. Provide both the substitution elimination product reach the following. Substitution product here. Anybody have something?
The BR was replaced with an OH, and it's now dash plus KBR.
That's an SN2 product. Yes, you said plus KBR. Yeah, that's also generated. That's your ions. Isopropanol, 2-propanol, just the solvent here. SN2 with inversion, I agree. What would be the elimination product here?
Double bond where the bond where the BR and the deuterium between those two, but BR would leave. No.
That there? Elimination product?
Yeah, because the other hydrogen is on the same side of the room, so it's not anti.
How'd we look? We're doing E2, right? Because we have strong base. E2 has stereochemical requirement. The leaving group and the beta hydrogen, or D, need to be what?
Anticoplanar.
Yeah, these are anticoplanar. The H here is not. We also have beta carbon here with an H and an H. Which one here would be abstracted if it did an E2 over here? This one, right? Anticoplanar, it will be if you can draw a chair conformation. Which one down here would be abstracted? The D. It would be anticoplanar. The non-circle ones are not going to be abstracted in an E2. Okay, you got a choice. Which one's going to be abstracted? The H or the D? Why H? It's a weaker bond, going to be an easier transition state in your rate determining step. Yeah, I would extract up there. That's going to be easier bond to break in the rate determining step. That's why I put the double bond up there. Both double bonds would be the same substitution. Disubstituted, disubstituted. So that's not going to, that's a wash. That's not a substituent. That's not a carbon substituent. That's just a funny H. Right? So we had a choice. Go with the one that's the weaker bond to break, right? Make sense? This would be E2 product. No stereochemical change here, right? No chemistry done down here, so it's still dashed, is that right? The deuterium was dashed down there? What we got here? Ethanol, silver nitrate, heat, substitution. It's going to be SN1 or 2?
SN1.
SN1, yes. There's no strong base. We know silver is to facilitate ionization and make carbocations, right? It's carbocation chemistry. So they have a substitution product.
Like racemic product.
Substitution product?
Racemic, something racemic.
Okay, I agree. If carbocation chemistry leads to racemic.
Is it just gonna be the same with the OH where this?
The OE, the OET would be where the CL is, and then you get AgCl and HNO3.
A lot of times just a star means racemic. There plus what? If we sort of show a full balanced line equation, line reaction, what are we going to form here?
Silver chloride?
Yes, silver chloride, not ACl. The silver is going to, silver chloride precipitate plus what?
HNO3.
I think you might have said HNO3. Ethanol is a solvent. It's going to be doing nothing.
Why would it be on that?
That's what I'm saying. You sure it's not supposed to move?
Mechanism. This facilitates ionization. I'm not going to show it complexing, but this comes off right. Boom, 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 boom. Cation here. This benzene ring, right?
Yeah, it's stable.
No, I don't like. Don't ever draw circles in benzene. Please do me a favor. Never do it. I'm proposing a hydride shift here. Right? A cation here, yeah, with one H there. Yeah? This is secondary. What is this? Secondary with resonance. What do we call such a cation next to the benzene ring? Benzylic. Haven't we always said if you can rearrange the cation to a better cation, always do that? Well, that's why I did it. Now the ethanol, weak base, well in this case nucleophile, attacks here, right? I'll call that phenyl, boop, 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 boop. Now we got the oxygen bonded with an ethyl and an H. You know the mechanism, right? Now something has to take the H. Well, the Cl minus is already tagged up with the silver, precipitated out. It's no longer in the equilibrium or the reaction. What can take the H? Well, you got this nitrate anion around, and that's what can take the H. Leave the electrons behind, so that's why I formed nitric acid there. Cation rearranged to a better cation, right? That's why I showed it over there. What would be the elimination product here? I'm just going to draw that as phenyl. Right? Phenyl. Boom, 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 boom. Elimination comes from the same cation as your SN1. Okay? If we eliminate it here, what would it be?
Double bond, double bond,
Double bond would be here.
and trans. So
It'd be trans, right? Why trans?
most stable.
Most stable. SN1 always gets most stable. That mechanism would be same thing, except instead of ethanol or instead of any of this adding here, you'd show something, even the nitrate taking the H, and these electrons moving in. We get the same outcome. We get this plus nitric acid. But this took an H from the beta carbon to put the double bond in. That's the second step of the E1, right? Taking the beta hydrogen. Anything can take beta hydrogen and E1. So that's a fast step there. E2 requires a strong base. Yeah? So that'd be the I would say this is your SN1 product and this is your E1 product. Okay, we made it to the double E2 elimination. No, it's not a new James Bond movie. Maybe one day. It's a way to make alkynes. Double eliminate. Two leaving groups. You treat this with a strong base, two equivalents, we can get an alkyne. Now, what's the intermediate? The intermediate is going to be an alkene. Okay? Let's look at this. What type of chemistry can we propose? First off, I'm using a very sterically hindered base to sort of promote elimination. It's also strong, so we are doing E2.
Take the right.
Does this leaving group, if leaving group out, there's a beta hydrogen here for this leaving group. This leaving group, there's no beta hydrogen there, one here. What we don't know is which happens first. Which leaving group is eliminated first, we don't know. If it was very symmetrical, it wouldn't matter because it would be the same intermediate. This one, I think it would matter. I don't know. I'm going to eliminate this one first. There's two here. Okay. Our tert butoxide, anion. Okay. Now we know this has a stereochemical requirement, but I'm not really showing any stereochemistry, so we don't really need to get into that. We're just looking for regio product. And that's going to give double bond there. The chlorine here. You see, what we don't know is, because there's no stereochemistry shown here, I don't know if this is going to be E or Z. I'll draw it sort of just like it's drawn there, and this ends up being the same side, Z.
It doesn't matter since it's not doing it.
Well, it matters, but you can only tell if we have stereochemistry. This is chiral.
Yeah.
I'm not showing you any stereochemistry, so you wouldn't be able to do a Newman, etc. So we don't know. And in this example, okay, but hopefully you do know what E and Z means, right? It could be the other one. It's not defined yet. That would give an alkene. Now, can we do another elimination? Let's draw in the H's. There's one H there and there's one H here. Call this one A and B. Which one is beta to the leaving group? No, HB. This is the carbon. This is the alpha carbon. Okay. Somebody please shout it out when you want to say something. Now we could take another equivalent of the base. Take the H. These electrons move in here and kick off the chlorine. What would that give? That's going to give, I'll draw the HA, alkyne. This all becomes linear now that it's the alkyne. And there we go. We eliminated HCl. And then we eliminated ACL again. Anybody have a problem with this second elimination?
The leading group is from, it's not tetrahedral.
Yes! That leaving group is not on a tetrahedral carbon. We said at the beginning of the class it had to be, right? Well, we've also said there's always exceptions to everything we say. But we recognize it, yes. The second leaving group is leaving from a trigonal planar carbon. Can you do that? Well, you did it in the lab yesterday and today, perhaps. It's more difficult. That's why the reaction you're doing this week, which is a double E2, requires 30 minutes of reflux at a fairly high temperature. And really 30 minutes is really not enough. It's better to reflux it for 2-3 hours. We just don't have that long enough time. It's very difficult because right there, Okay? The leaving group is on sp2 carbon. All right? Now, this, as I drew this alkene, the H and the Cl are anticoplanar. Trans. See how these are trans on the double bond? And it's all planar. Trans. If I had drawn it in a E form, they would have been syncoplanar. If they were syncoplanar, can the reaction happen? No, it can. We didn't say, we never said it could not happen. We just said that transcoplanar was favored. The one below, the leaving groups are on the same carbon. Because they're on the same carbon, there's only one intermediate that's going to be formed because there's only one beta carbon. Hydroxide takes the H, moves in, and we kick off one leaving group, either one. Right? What is that going to give? Double bond there. What's on this carbon now? One bromine is there and one phenyl. And over here would be an ethyl. This has stereochemistry though. It's actually should probably be a mixture because there's no stereochemistry here. Should probably be a mixture. This is bromine and carbon are your big groups, so this is Z. You're probably also going to get the E here. Don't worry about this too much, other than the fact that it is stereogenic. All right. Now there's an H here. Can we now eliminate HBr and make another pi bond? Well, we did it once. Let's just do it again. Boom, boom, boom. Again, this ends up being anti-transcoplanar. And what does that give? We now have triple bond here. This carbon has a phenyl. This carbon has an ethyl. Right? Alkyne is all linear now. We did a double E2 elimination. Intermediates, though, here are alkenes. And yes, we're eliminating, from there, we're eliminating the leaving group from the alkene carbon, as we mentioned. That's why this tends to be a little bit difficult, but doable.
Would BR2 form
Do what?
with BR2 form with the leaving
Okay.
bromines? The leaving bromines, would they bond with one another? BR?
No, because they left as Br minus.
Oh,
These are not going to bond together. You got too
are
many
they just going
electrons.
to be?
No, and this, if you want to balance this out, you're going to make two equivalents of lithium bromide.
Oh,
And you also make two equivalents of what?
8 water.
Water, because hydroxide took CH. Two equivalents of water, two equivalents of lithium bromide. A little final exam review. We'll talk more about it. Okay, test on Monday. What do we got? We started with resonance. Yeah. After resonance, we moved into chemistry of dienes, 1,2, 1,4 additions, etc. There we also had Diels-Alder reactions. Then we moved into what? Mass spec. Yeah. Plenty of problems with mass spec in the workbook. We did cover UV vis. Yeah, there'll be some there. Then we got into substitution and elimination. Those are the main broad topics, right? Similar format as before. Nomenclature, what did we do? We did dienes. Yeah. So there will be mass spec, similar to like in the workbook. Could also maybe combine IR with mass spec. There's one or two like that in the workbook. Questions about anything? I got one last thing to show you. Quiz will be posted upstairs.
Is our lab going to be due Monday or Wednesday?
It'll be due Wednesday in class. Lab sheet for the double E2. Wednesday in class. Okay, guys. So there's a good amount of decision making. Hopefully you're getting more comfortable with it. There are diagrams available to help with decision making. I don't know does that help some? Yeah? Okay. Predicting substitution elimination, E1, E1, SN1, SN2, etc. outcome. First question, is there an tetrazine requirement with a leaving group? Because if there ain't, you ain't doing any of these mechanisms. Unless you want to talk about an exception we just showed here. Okay. All right. So if there is, then all these are possible. If not, game over. Next, is there a beta hydrogen? If not, then E1 or E2 is not possible. Have you ever thought about that? If there's no beta hydrogen, you can't eliminate. Right? May not have never thought about that. If there is a beta hydrogen, well, all four are still possible. Right? You ever thought about that? Anyway, let's go if you need. We're about out of time. Let's go. Is the beta hydrogen coplanar with the leaving group? If not, or never, E2 is not possible. If so, well, they're all still possible. Is there a very strong base? If so, they're saying E2. I said it would certainly be bimolecular with something strong. Typically, super strong bases prefer elimination. I didn't really say that, but well, see, very strong. They're saying E2. I really didn't say it. Strong. What did we say? Bimolecular. E2 or SN2, right? Bimolecular. Okay. It's all here. Let's show something else. Solvent. A product. They're saying SN2. We really didn't do that. Heat. Here we go. We did this. Heat. Are you heating? Yes. What's favored with heat? See, elimination. If not, SN1 tends to be more favored. Okay? It's all here. I don't like to give you guys this, especially up front, because you tend to want to just memorize it and not really try to struggle and learn it. Would you like to see this by email or something?
Yes.
Please, you can't start memorizing the details. Learn, work with it, okay? See some of you in lab this afternoon.